Hey guys, welcome back to chapter 15. What we're going to do in today's lecture is we are going to explore this idea of the equilibrium constant. So again, we've got our chemical reactions that are in a dynamic equilibrium. So the rate of the forward equals the rate of the reverse. We've got this equilibrium constant K, and that equilibrium constant K gives us a little bit of indication as to where the equilibrium lies. So do we have a high concentration of products, or do we have a high concentration of reactants, or does it seem like they're both kind of equal? Okay, so we're going to look at this equilibrium constant K today. So the equilibrium constant is denoted with a capital K. I've put this lowercase c here, and that's just the equilibrium constant. When we get to the acid and bases chapter, that's going to be important because we'll have an A when we're talking about acids. We'll have a B when we're talking about bases. And a C is just kind of a generic reaction. It's not an acid or a base. So if you see that subscript C, that's all that means. So as I said, the equilibrium constant is a measure of how far this reaction proceeds. So first, here's our generic reaction. So A reacts with B to produce C and D, and then we see our equilibrium arrow. These lowercase a, lowercase b, those would just be our coefficients. So we would say 2A reacts with 1 molecule of B, so on and so forth. Okay. So how do we go from a chemical reaction to this equilibrium constant K? Well, it's going to be the concentration of the products over the concentration of the reactants. So products over reactants, okay? So we're going to take the concentration of our products, so concentration of C times concentration of D, and we're going to raise it to the power of the coefficient. So if this was a 2, C would be squared. If this was a 3, D would be cubed, okay? So concentration of products over concentration of reactants, so we're going to do the same thing. So concentration of A times concentration of B, and then whatever the coefficients are, we're going to raise it to that power. This K, because we're taking a ratio of concentration, the K is unitless, so there's no units associated with K. And then this K just has this formula has a fancy name. It's called the law of mass action. The only reason I put that up there is if you see that on Pearson or in Chem 101, you see the law of mass action. It's just a fancy way of saying equilibrium constant problem. Okay. All right, so let's do an example. Let's see if we can write the expression for K for the following reaction. So K is going to be the concentration of our products over the concentration of our reactants. So K equals... my products, I've got CO2, so that's going to go on the top. And then whatever the coefficient is, I'm just going to write that as the subscript, so squared. Over the concentration of my reactants, so carbon monoxide times oxygen. And again, I see a coefficient of 2 with carbon monoxide, so I'm going to square that. And then here there is a coefficient. There is an implied 1. So when I do oxygen, I can imply that, or I could explicitly write out the 1 there. Okay, so that's all we need to do to write the equilibrium constant expression for this reaction. The slideshow walks you through it. Okay. So why don't you guys try a couple? Why don't you go ahead and pause the slideshow and see if you can write the equilibrium constant for the following 2 reactions. All right, so we've got products over reactants. So for the first one, equilibrium constant K is products, which is NH3. And we're going to square that because of the coefficient. Over reactants, so N2 times H2, and that's cubed, and that has a 1. For the second one, we've got equilibrium constant K is products, so CH4 to the 1, H2S squared divided by CS2, 1, H2 to the 4th. Okay. So easy peasy writing the equilibrium constants K. You'll do this so much in this chapter that you'll be able to do it in your sleep. All right, so let's talk a little bit more about the meaning of K and determining K. So what we see here is some data from a chemical reaction. So data from something that a lab that somebody did. So let's go through this table. So here's the initial concentrations. So we've got hydrogen and iodine react to form hydroiodic acid. So here's our initial concentrations. Here's our concentrations once equilibrium has been established. So what you see is that in each trial 1, 2, 3, 4, 5, they varied the number of, they varied the concentration of each of the items. So here we had all reactants, no products. Here we had no reactants, just the product. Here we had equal concentrations of each, and then we just did some different variations, okay? Then we let this go until it found its equilibrium, and we see our equilibrium concentrations. So just glancing at the numbers on this table, it doesn't really look like there's any pattern, rhyme, or reason to it. But if we were to calculate the K value for each of these trials, what we would find is that the K value should remain constant. So how would I find what K is? So the first thing I would do is I would write the equilibrium constant expression. So K equals, here's my reaction, products, so HI squared over reactants, H2, oops, that's an H, I2. And then to determine K, I would just plug in the concentrations at equilibrium. Okay, so once this has gone to equilibrium, then I'm going to plug it in. So for this one, the equilibrium concentration for HI is 0.78, and don't forget to square that. Equilibrium concentration for hydrogen is 0.11, and for iodine is also 0.11. Okay, so let me just clean this up a little bit. So I'm going to take first 0.78 squared, 6, we'll call it 1, because I'm running out of room. And then we'll take 0.11 times 0.11, and that is 0.012. And then we'll divide those two numbers. So KC is going to equal 0.61 divided by 0.012. Equilibrium constant K is 50.8. And again, that's unitless. Okay. If I were to pick any of these trials, so I just happened to pick trial 1 because that was at the top. But if I pick trial 3 or trial 5, and I did this same math, the equilibrium constant K should come out to 50.8. So let's take a look at the data here. And that's exactly what we see. So they've crunched the numbers for each of the trials, and the K value came out to 50 each and every time. So what this tells us is that the initial concentrations of anything in our reversible reactions, initial concentrations doesn't matter. The system will always find the equilibrium. And when it finds the equilibrium, the K will be the same, will be a constant, right? Not that the concentrations are all going to be the same, but when we take the ratio of the concentrations, those will always be the same at a given temperature. And we are going to prove this in lab. So this is one of the things that we're going to do is look at a series of reactions, let them get to equilibrium, take a look at them, and then we'll solve for that equilibrium constant K. So let's take a look at an example. So I quickly calculated K for you in the previous example. So why don't you guys go ahead and pause the video and see if you can determine what the K value is for this reaction. All right, first step is to, get a pen. First step is to write the equation for K. So concentration of our products squared over the concentration of our reactants, NO squared, BR to the 1, okay? What is the value of K if the equilibrium concentrations are as follows? So now we just plug in chug. So plug in the numbers, chug through them. So our product is 0.47, and we're going to square that. NO is 0.31. We're going to square that. And BR is 0.24. So let's just clean this up a little bit. I've got 0.47 squared, and that's going to be 0.2209. I have room. That's why I kept all the decimals this time. And the bottom is 0.31 squared times 0.24. And this is 0.0231. And then we divide those. So 0.2209 divided by 0.0231. And the K is 9.6. Okay. Pretty easy, simple, straightforward start to the chapter here. All right, so now that we know how to calculate for K, let's take a look at what in the world this K value tells us. So what does 9.6 even mean? So remember, K tells us how far a reaction is proceeding. So is it reactants favored, not much of it reacted? Is it products favored, a lot of it reacted? So let's take a look at that. Okay. So if we have a lot more products than reactants, so we look at the concentration of the products, we look at the concentration of the reactants, and we're like, wow, most of that became products. I have a really big number for the concentration of products. Our Kc value is going to be greater than 1. And that tells us that our forward reaction is favored, or our products are favored. So if we have a really big concentration of products, small concentration of reactants, certainly that's favored. And when we calculate that out, we'll have a big number on top, little number on bottom, and of course that's going to be greater than 1. Okay. Key thing to point out here, key misconception. Just because K is big does not necessarily mean that it's fast. So this is a completely separated chapter from kinetics when we talked about the speed of the reaction. So the forward reaction may be favored, but it doesn't necessarily mean the forward reaction is fast. It just means that once it finds equilibrium, however long that takes, once it finds equilibrium, it will be products favored. Okay. Let's look at the opposite. So let's say we mix the two together, we take a look at the concentrations, and what we find is that we have a really big concentration of reactants, a really small concentration of the products. So in this case, lots of reactants, just a little bit of products. That means Kc is going to be less than 1. So big number on the bottom, little number on top. That's going to give us a decimal. And the reverse reaction is favored. So reactants are favored. So we'll see the equilibrium lies over here with the reactants. So we've looked at Kc's bigger than 1. We've looked at Kc's smaller than 1. There's one more scenario we need to talk about, and that's when Kc equals 1. So if we look at the concentration of reactants and we look at the concentration of products, and they're basically the same, so the products would equal the reactants, Kc would be basically 1, and neither direction is favored. So in this case, this is probably the most friendly one because this is what our brain wants to do. In this case, the equilibrium lies right in the middle. So we don't have reactants favored or products favored. Once it finds equilibrium, we have equal amounts of each. So that's what happens when Kc equals 1. Okay. So what I want you guys to do in this example is I want you to determine the value for Kc. And then I want you guys to think about, does this reaction favor the reactants or favor the products? So go ahead and pause the video and solve. All right, step 1 is to get the equation for Kc onto the paper. So Kc is products over reactants. So our product is cobalt chloride. Oops. And our reactants are cobalt and chlorine. Don't forget to square that chlorine. Okay, so it gives us the values. So now we just need to plug and chug to get to K. So our products, the concentration is at equilibrium is 1.24. Reactants, our cobalt is 0.234. Our chlorine is 0.355. Don't forget to square that. Okay. So let's clean up the bottom. So nothing to do on the, whoopsies. So nothing to do on the top. So just rewrite that. But let's go ahead and clean up this bottom here. So 0.355 squared times 0.234. And the bottom is 0.02, say 95. So 1.24 divided by 0.0295, and we get that Kc equals 42. Okay. So what does that 42 mean? Well, 42 is a number that is bigger than 1, okay? And so what we see here is our concentration on top is much more than our concentration on the bottom. So that gave us a number greater than 1. So that tells me that the forward reaction is favored, or the products are favored in this case. So when we mix these two together, most of these are going to push and create cobalt chloride. There'll be a little bit of this left, but not much. So that's it for our introduction to K and for calculating the value for K. Hope you guys found this helpful.